today's lecture we're going to finish off our work on differential equations. And this is the idea we looked at yesterday. In particular, we learnt how to solve this general setup of an equation. So we learnt how to solve something like y double prime plus 2y prime minus y equals 0. The basic idea, thanks to the shushes. The basic idea was to reduce the analysis down to quadratic, right? Look at the roots of the quadratic. Are the roots real and equal? Are they, real and unequal, real and equal? Are they complex? Depending on which case you've got, the general solution kind of varies accordingly. So in today's lecture, we're going to consider this more general problem where you have some function of x on the right-hand side. See, there's 0 here, but this could be something like x squared or cosine x or something like this. Now, in terms of applications, this kind of general problem leads itself to modelling, I guess, mass and spring systems where you may have damping and or an external force. So the f of x could represent an external force being put into a system, a vibrating system. Now, the reason we solved this more simple problem yesterday is because you actually use the techniques from this to solve this more general problem. So it's very, very important that you get the solutions to these kind of problems down pat. So just to remind everybody, the analysis for this homogeneous problem, guys, shh, please, shh. The analysis for this homogeneous problem that I've underlined up top just reduces down to the analysis of a quadratic. You look at the roots, right? If the first case happens, if the roots are real and not equal, then it's exponential functions. If the roots are real and equal, well, it's exponential functions again, but you've got that little x hiding in there. And thirdly, if the roots are complex, then it's a combination of exponentials and cosines and sines. All right, so on to the slightly more difficult case. Now, if we have a solution to the homogeneous problem, and we can construct somehow another solution to the more general non-homogeneous problem, then the following fact's going to be really important for us. If you add those two functions together, they form a general solution to the non-homogeneous problem, NH. So I've justified it there. Essentially, you just differentiate this twice and rearrange some of the terms, and you use the fact that since y1 satisfies the homogeneous problem, all these terms add up to 0. So you're just left with f of x. So the basic idea that we're going to look at is solve the corresponding homogeneous problem that we looked at yesterday, construct a new solution to the more general problem, and add the two functions together to form our general solution. So how does it work? Well, let me show you. So in this case, our f of x, our given function of x, is just a simple function 2x plus 3. We're going to firstly solve the homogeneous problem, right? So we set that equal to 0 and solve the problem, just like we did yesterday. Right? So y sub h, I'm going to write as, that's going to be the solution to the homogeneous problem. So you set f of x equal to 0. Now, we solved this problem yesterday. The characteristic equation is lambda squared minus 5 lambda plus 6 equals 0. So we can factorise that and get the roots, right? And so our roots are going to be lambda equals 3, lambda equals 2. That is, our roots are real numbers, they're both real numbers, and they're not equal to each other. All right, so as a result, our solution to the homogeneous problem is just a linear combo of exponentials. Okay, so that's the first part of these more general problems. Just what we looked at yesterday. Now, the second and slightly more challenging aspect is that we need to somehow construct a basic solution to our original problem. So how do we do that? Well, it's all based around the structure of this function. You can see this is just 2x plus 3, right? Just a simple linear type function. To construct y sub p, the particular solution, just keep it in a similar or same format as that 2x plus 3. Let me show you what I mean. So, to construct y sub p, a particular solution to this problem, we base our choice on the form of our given right-hand side. So it's 2x. Yes?
What is yp again?
It's defined as a solution to the particular. It's a particular solution to the original differential equation. Okay? Yep, correct. Right, so if this is, say, start, so let's make our initial choice, our initial construction, the same style as that f of x, 2x plus 3. So let's choose it to be, I don't know, a constant times x plus another constant. Okay, this is the same, but more similar but more general format. So what we're going to do now is determine big C and big D, and then we've got our particular solution. So for this choice, if I differentiate, I'm going to get C, and the second derivative is just 0. So what I'm going to do is take this, and this, our original choice and their derivatives, and sub it back into my original problem that I'm trying to solve. All right, so what are we going to get? So the second derivative, 0, minus 5 times the derivative, plus 6 times my original construction. Oh, okay, sorry. Whoops. It's a solution to this problem, right? So you need the 2x plus 3 on the other side. Whoops. Okay, so what we're doing here, we're trying to find constants, big C and big D, that forces this to be a solution, a simple solution to our original problem. Okay, so all we really need to do now is somehow simplify this setup here. All you need to do is equate the coefficients. So all the x's on one side have to equal all the x's on the other side. All the constants on the left-hand side have to equal the constants on the right-hand side. All right, so we're going to get 6cx equals 2x, so 6c equals 2. And we're going to get 6c equals 3. So all we need to do is solve those for big C and big D, and you've got your constructed particular solution. You've got your y sub p. Okay, so y sub p is going to be 1/3 x plus 7/9. All right, so this is our solution to the homogeneous problem. This is our solution to a particular solution to our original problem. What the previous slide said is once you're at that position, the last thing you do is just add the two things together to form a general solution to the original problem. So that's the last step. So it's going to be a e to the 3x plus b e to the 2x plus 1/3 x plus 7/9. That's it. So it's not a massive leap from what we did yesterday. Okay, you're still looking at that homogeneous problem with a 0 on the right-hand side, but the extra step just involves constructing a particular solution, y sub p, to the original problem. Take the two functions, add them together. That's your general solution. Yes?
What is the general solution of some of the homogeneous and particular solutions?
Why? Good question. Okay, that was on the previous slide. The question was, why do I have to do that last step? Why do I have to do that last step? Why do I have to add these two things together? It comes back to this, okay? If this is a solution to the homogeneous problem and this is a solution to the non-homogeneous problem, you can just show that they satisfy, the sum of them satisfy the differential equation, okay? Any other questions? All right, so where does that sit on the difficulty scale? Medium. Medium. Let's look at another one. Here's another differential equation, but you can see the right-hand side's changed. It's not, some sort of polynomial. It's an exponential function. So how does that change our setup? On the left-hand side, these are equal, but these are not. So we're going to have to somehow adjust our construction for y sub p. So let me show you. So from our previous example, the solution to the homogeneous problem is just the same. What we're interested in here is, well, okay, how do I construct the particular solution to this problem? Then I've got to add them together, right? So look at the structure of the right-hand side. Look at the structure of the right-hand side. It's an exponential function, right? So can anyone suggest what might be a suitable construction for y sub p, a particular solution? Anyone? an exponential function. So maybe like a constant times e to the 5x. Let's try that. Now note, and this is important, note I've still kept the 5x. Okay, you don't need to change that. It's just the coefficient that I'm just going to set as a constant. Let's differentiate. We're going to get 5c e to the 5x. If we go again, we're going to get 25c e to the 5x. So let's take those and sub them in the left-hand side of that original equation. So what we're trying to do here is find a constant c so that this satisfies our original equation. That's all we're doing. All right, so y double prime is this minus 5 times y prime, which is this, plus 6 times this. And that has to add up to 12 e to the 5x. So what c will make that happen? 2, yeah. So if we simplify, c equals 2. Thus, our particular solution is just 2 e to the 5x. So let's add those two functions together and produce our most general solution. 6. So you're going to get 25 minus 25. So that's going to disappear. You're going to get c equals 2. So our final step, our general solution is just this. Right, not difficult. Not difficult. Oh, good question. Question is, what about those A and B's down there? What are those? Can anyone suggest how we might find big A and big B? Initial conditions, right? So do we have any initial conditions there? No. So that's the best we can do at the moment. That's the best we can do. Now, here's a question for everyone. What happened if I, in that problem, if I calculated my y sub p and it was something like 2e to the 2x? 2e to the 2x. What do you reckon? Can anyone see a problem with that? Anyone? Anyone? Yes? Yeah. So can you say some more? Yeah, very good. Okay, one thing you need to be careful of in these problems is if you calculate this y sub p, this particular solution, you construct it somehow, but it's already contained in your y sub h, then when you add the two things together, the second thing isn't bringing anything new to the table. You're just adding something that you've already got. So you need to be very careful when constructing this y sub p, because it may or may not bring new things to the table. You want it to bring something new, otherwise why add the two things together? You're just adding something you've already got. So let me have a look. We'll have a look at that in a minute, but before we get to that, here is a little table I've produced. for the construction of your y sub p, your particular solution. So if you've got a polynomial on the right-hand side, well, you make your construction a general polynomial. If you've got an exponential, make your construction an exponential. Now here's a little twist though. This is important. If your right-hand side was something like cos 2x, you would think, oh yeah, let's make a choice, I don't know, a constant times cos 2x. No, it's not general enough. So what you need to do in that case, let's say this was 1, is have a combo of cosine and sine. And I'll do an example that highlights why you need that in a minute. Okay, so loosely speaking, what you do is you look at your right-hand side and you see the structure of it. Is it a polynomial? Is it exponential? Is it a trig function? What is it? And then based on its structure, that's how you construct your y sub p, your particular solution. So let's do a problem, see how it works. All right, so you have to be careful. You have to be careful. Now again, this left-hand side is the same as the previous examples I've solved. So I'm not going to go back and do the y sub h. But the question is, what is the particular solution? What is the particular solution? So now, what we would, I guess, initially think is that I could choose something like, I don't know, a constant times e to the 2x, but you've already got a constant times e to the 2x. So in this case, if you added the two things together, you wouldn't be bringing anything new to the table. Okay, so one way to get around this is the following. Just multiply through by, in this case, the x variable. Cx e to the 12x. So you can see this isn't contained in this. So what I want to do now is form that constant c somehow. Oh, sorry, the 2x. Sorry. Oh, y sub p. Okay. So can we find a constant that will make that bottom line a solution to my original equation? Well, we can differentiate this a couple of times using, say, the product rule. And you can get the following. I'm not going to put all the details down. And then you take these and sub them into the left-hand side. Then you can form your constant c. So I'm not going to put all the details down, but you do get a constant c equals minus 12. So our constructed solution, our particular solution, is just the following. So now we just take our two solutions to the homogeneous and our particular solution, and add them together. Okay, now that's slightly annoying, that problem. Why? Because you've got to go through and do a bit of differentiation and then a bit of back substitution. It's a bit longer than the previous example. Okay, so it'll take you a little bit more time. But lots of students, they see something like this on their end session exam. They make this choice and they find out that they can't find the constant c. If you make that choice y sub p equals c e to the 2x, you'll differentiate it a couple of times, plug it into the original equation, and you won't be able to find c. You just can't find it. So even if you make a mistake with your initial choice, you should know about it by the time you come to calculate c. Just multiply through by x. All right, here's another one. Same sort of setup, but different homogeneous solution for this one. Okay, so we solve the homogeneous problem first. Okay, so to do that, we write down the quadratic, look at the roots. The characteristic equation. Okay, it's lambda squared minus 4 lambda plus 4 equals 0. So our roots in this case are 2 and 2, right? It's a repeated root. So what's our solution going to be? It's going to be a e to the 2x plus bx e to the 2x. So that's half the problem done. Now we need to make a choice. So I'm confused. The idea that we just used won't work on that problem. Because you go, all right, well, for part 2, what I want is something like 2e to the, a constant times e to the 2x. Can anyone tell me why that won't work?
Second term again.
Yeah, right. So e to the 2x isn't going to be a good choice, or a constant times e to the 2x isn't going to be a good choice. A constant times x times e to the 2x isn't going to be a good choice because that's in y sub h. So what would be the logical thing to do? Just multiply through again by an x. Okay, so a choice here would be a constant times x squared times e to the 2x. So just keep going until you don't get anything in your y sub h. That's it. So let's try that. Okay, important. If you don't make that construction properly, you're not going to be able to answer the question. So we're going to calculate our derivatives. And back substitute those in. Okay, I'm not going to calculate all the derivatives. We end up with, in this case, c equals 1. So this is our particular solution. So assuming we can get that far, let's just add the two functions together. So you should fill in the details here. Calculate these derivatives, plug in this side, and you'll be able to get your constant c. All right, so that's my homogeneous solution. All right, so this is exactly what I've been trying to point out. If the right-hand side, if the right-hand side of your differential equation appears in your homogeneous solution, then you have to multiply through by x or x squared just to force it out. Now, here's a really good example. You can see in this example, we've got cosine x on the right-hand side. We've also got some initial conditions. So let's go through and completely solve this and see what's involved. All right, for part I, the homogeneous problem has solution a cos x plus b sin x. I'm not going to do that. We know how to do that from yesterday's lecture. Write down the characteristic. In this case, the roots are going to be complex. So you're going to get a combo of cosine and sine. The more interesting and more difficult part of this problem is the particular solution. Now, because this is a cosine over here, it'd be tempting to just say, oh, let the particular solution be something like c cos x. No, it's not going to work out. So what we need is like a linear combo. C cos x plus d sin x. And you'll see where this comes up, why we need those at the end. Right, let's calculate the derivatives. So it's going to be, what did I nearly do then? What's wrong with that? Y sub p? Can anyone tell me? What's wrong with it?
It's in
Yeah, exactly. So that's not a good choice. So let's just multiply through by x and try that. So with that choice, hopefully we're okay. We want to calculate the y dash of p and y double dash of p, the two derivatives. Okay, so that's our first derivative. Let's calculate the second derivative. Okay, so it's a bit of a mess now. But what you can do is back substitute here and here. And you can see if we add this and this, firstly, it's going to cancel out, right? So we're going to be left with these. So let's give this a, I'm just going to go back to star. So now what we want to do is determine big C and big D from that boxed bottom line. So if you look at it, big C is going to be 0 and big D is going to be something like a half. Okay, so now we can put everything together. So we combine our homogeneous solution with our particular solution. All right, y sub h, that's up here. And y sub p, well, c is 0, so that's going to be to 0, and that's going to be a half. But I'm still left with something. I haven't got big A and big B. So I need to incorporate those initial conditions, right? So can you, come on man, wake up. There's only like 7 minutes to go. You can do it. Big A and big B can be calculated from the initial conditions, right? The initial conditions. So just differentiate, plug in x equals 0, originally plug in x equals 0, and you'll get big A and big B. And B equals 0. So, what's our final answer? Our final answer will be 3 cosine x plus x onto sine x. Now, if I just made a choice Say if I'd left off the sine x here, I wouldn't get that. All right, any questions?